Hello everyone. Welcome to another GDS webinar. I'm happy that you were able to join us today. So let me just share a little bit about who we are and about our series. So we are the APS topical group on data science, and we are a new group for the American Physical Society. My name is William Ratcliffe. I'm the secretary, and Jay Rin is also with us, where she is the chair. So we've had a number of past webinars that are all available for your viewing pleasure on YouTube. This one will be as well. If you want to stay connected to us, you can follow us on social media. There are a number of ways. Either join our Slack channel. We'd really love to have you. You can help us plan these events, and you can also get involved with GDS in other ways. We're also active on Twitter, Facebook, LinkedIn, etc. One important thing is that as a new unit, we have almost no funding. And so we do obtain funding through the kindness of people like you who actually become GDS members. So at the top, there is a link to become a GDS member if you are not one already. I believe it's like around $10. Again, times are tough, and so I realize that not everybody can join, but if you are able to join, then we would really appreciate it. So today we have a number of excellent speakers, ranging from Alex from Google to Pratyush from the University of Maryland. And we'll get started in one moment, but I'd also like to just do a brief poll to see see where you guys heard about us from. After that, then we'll get started with our first speaker. Alex has been experiencing a little bit of technical difficulties, but we'll see if those are resolved. Otherwise, we may have to change the order by one. So here is our quick poll. And we'll just do this very briefly. Okay, we see the numbers coming in. We're at 65% of people have voted. We'll give you just a few more seconds. Wow, 67, 68. Okay, you guys are awesome. Thank you so much. 75. I noticed that we have a question. Jay, my view is a little bit limited. Okay.
Right.
We're at 78%. I think we've saturated, so I'm going to close the polls. Okay, and
yes, William, this is Jay. I can follow up with the question offline. Yeah.
Okay, perfect. So we've closed the poll, and so now I'll just ask a quick question. Alex, do you want to give this a shot?
I am unsure if I can anyone see me now or no? Am I visible? I have tried to connect to the meeting with the presentation software. I'm trying to see if I can figure out now how to present.
So I've just made you. I've just made you the presenter.
Okay. I could try to. Do I have audio? Do I have audio through here? Or?
You have audio.
Okay. Then I'm going to try this. I'm going to come over here. I'm going to do this. I'm going to come over here. You can see my screen. Is that right?
I cannot see your screen.
Not see my screen. Okay, I'm trying to pull up my presentation and trying to present it.
So there should be an option to share your screen.
Yeah, I think I tried to click that.
Okay, perfect. That worked well. Okay, I think we're in business. So everyone, Alex just had a problem because he was running on Linux, and so we're not aware that Linux actually apparently is not supported by GoToWebinar. So please send them your complaints. So just a brief introduction. Alex is a senior research scientist at Google. He is a recovering physicist focused on the intersection of information theory and deep learning. He got his PhD from a sort of new friend of mine, Jim Setna at Cornell. And let's go and hear his exciting talk about thermodynamics of machine learning. Let's get started. So Alex, we'll turn off our webcams. If you can turn yours on, that is great. If not, that's also fine. I'll turn my cam back on in 30, at the end, at the time where you're supposed to start taking Q&A, and so that will be at approximately 1:35. All right, so let's get started. I'm going to turn off my camera.
Okay. I mean, I am currently, trying to show my presentation, which doesn't seem to be coming up. While this loads, I guess I can just kind of start. Oh, here we go. Presumably you can see this thing on the side. Here, I'll try and get that out of the way. All right, we'll see if this works. This isn't the right version of my slide. That's okay. Okay, so hi everyone. I'm Alemi. I'm a research scientist at Google, and today I wanted to tell you a bit about a project that paper I wrote a couple of years ago, Thermodynamics of Machine Learning. And in the course of the next sort of half hour, that's I think what we're going to try to do. I'm going to try to build up a thermodynamics of machine learning, whatever that means. So in detail, I think I'll break it down. At the beginning, I'll try and do a overview, a sort of a refresher on thermodynamics and system mechanics, but sort of a propagandist view that will set the mood for later on. Then I'll try to convince you that there's a general calculus for deriving objectives in machine learning, analogous to thermodynamics, and make a connection to things you may have heard about, and time permitting, go on from there, talk about analogies and results. So, okay, here we go. Let's start. Thermodynamics and statistical mechanics. Now, I know you know this. Let's talk about it in a particular way. So let's say I have a physical system. Physical system has configurations. It has a bunch of states that it can be in. For something like a gas, this is all of the positions and velocities of all of the particles. Now, I don't really care what state the system is in. I don't care about the precise positions and momenta of all the particles. Instead, they're state functions. They're sort of extensive properties that I do care about. Things like the energy, volume, number of particles, length of a wire, area of a bubble, magnetization of a magnet. These are the things I actually care about. And thermodynamics is about trying to do inference, trying to make predictions about what those extensive properties are without complete knowledge of the state. Because I'm ignorant about what the true state of the system is, and even if I knew it, I can't write down 10 to the 26 positions and momenta. So because of that ignorance, let's manifest that ignorance, let's make it manifest, and instead of trying to describe the actual state of the system and its dynamics, let's describe a distribution over all possible states. In a subjective sort of sense, let me describe my degree of belief about what state I think the system is in. That's the distribution over states, P of theta. And now that it's in a distribution over states, it no longer has a well-defined value for the state functions, but I can describe their average values, their expectations over this distribution. And we can keep going. Now that I've made it manifest, I can actually quantify my ignorance, and we can add one more functional, the entropy. The entropy is a number that I can calculate that tells me how ignorant my description of the state of the system is, right? It's measured in bits. It's a measure of like how many yes or no questions I would need to answer in order to determine what state the system is in, provided that I had a certain set of degrees of belief about what states it could be in. And once I do this, now that I've kind of invented this new functional, if you give me your set of beliefs, you give me a distribution over all possible states, then we could calculate the average value for all of these extensive quantities, as well as the entropy. And that's going to be a single point in this space, right? You give me a distribution over states, I get an expected U, an expected V, let's say, if I just do two of them, and an S. That's a single point in some n plus one dimensional space. Now, instead of describing a single set of degrees of belief, now try to imagine all possible distributions over states, right? all possible changes to your beliefs of the state of the system, all possible weights for all possible states of the system. And that'll start to move around. It'll start to fill this three-dimensional space. But there's going to be a boundary. There's going to be an edge, my fantastic rendering of which is on the right. There's going to be some boundary to this three-dimensional, in this case, three-dimensional space. It's going to be a two-dimensional surface. And those are special. Those are extremal. Those are, optimal in the sense that, like for instance, if you fix the average energy and average volume, there will be some distribution that is maximally ignorant, that has maximum entropy, that has no structure. It has nothing else that you use to describe that distribution except its average quantity. So this optimal, this Pareto optimal frontier of maximally ignorant distributions over states, this two-dimensional frontier, you could describe as a two-dimensional surface, and that's going to be special, right? That surface is a geometric object that will have derivatives and things like that. So here on the right is my terrible rendering of one of these things. Here's an actual one, the plaster mold created by Maxwell based off a paper by Gibbs. It's an actual thermodynamic surface. This is what thermodynamics is about. Physical systems have a sort of geometric object that describes the relationships and trade-offs between extensive variables in the maximally ignorant sense. And thermodynamics, especially undergraduate thermodynamics, is really just sort of like a sadistic exercise of naming all of the multiple, equivalent ways of describing this single geometric object. For instance, instead of describing it as, entropy as a function of energy and volume, I might describe it as energy as a function of entropy and volume, or I might do any of the other things. Because the surface is convex, because like entropy is a convex quantity, instead of describing points on the surface by their coordinates, I could describe them by their derivatives, right? You can do that like a Hunter transformation. Not only in thermodynamics, we name all of the derivatives, we name all the second derivatives, and we name all of these different transformations, right? Instead of the energy, the free energy, the Gibbs free energy, the Helmholtz free energy. But these are all ultimately different ways to describe a single geometric surface that characterizes the behavior of a physical system. Part of the reason we name all of them is that they're useful, right? Like susceptibility, certain second derivatives like thermal conductivity are useful for telling the difference between things like metals and wood, right? Different kinds of physical systems have there's zoology, there's different kinds of surfaces that you could create. That's thermodynamics. To go beyond just that kind of bulk property, you could also characterize the kinds of distributions that live on the surface, right? It's the solution to a certain extremal problem, like an action principle. What are the states that are maximally entropic given some known value of their expectations? You can solve that constrained optimization problem, and the solution is always a generalized Boltzmann distribution. If you're not familiar with this kind of way of talking about information theory and statistical mechanics, I highly recommend you check out the paper by James. It's really, really fantastic. Okay, so that's thermodynamics. It's a way of trying to describe and make inferences or predictions about how materials in the world behave and make trade-offs between these extensive quantities without full knowledge of what all their internals are. We're going to try to do the same thing. Let's try to look for the same kind of like variational principle or extremal principle that we could use to describe machine. Okay, so now a kind of unfair overview of what machine learning is in the context of general model. In the beginning, you have data, images, and labels. Okay. And you might be interested in telling whether things are dogs or cats or hot dogs. And if you were sort of a Bayesian, what you would do is today, you do sort of maximum likelihood, you write down a general model. You would try to build a machine that you think can create the images and labels, that can create the data with a billion knobs, and you would adjust all the knobs so that the likelihood that you observe the data that you do observe, the real world data, is as large as possible. That's machine learning. I mean, that's generative modeling. That's Bayesian inference. But it's also wrong. It's a lie, and we sort of know that it's a lie. The data didn't actually come from your process, right? You don't actually have the correct machine that gave rise to the data. The universe created the data, and you're just trying to describe it. And it's always bothered me coming to physics that sort of machine learning starts by imposing their will on the world, right? Assuming that they know the true process that gave rise to the data. I know, our models in physics are always wrong, right? Mother Nature is more clever than we are. We can only hope to kind of approximate it. So this has always really bothered me. And so let's try and look for an extremal principle or something that we can use to guide our, that's different, that doesn't lie. Let's try and look for sort of the analog of the thermodynamic surface. Now, I'm not going to be able to go into all the details, but the next thing that I want to land is that there is a calculus, there is a crank that you can turn that you can derive these kinds of objectives, and they lead to information theoretic things. The ingredients for that kind of thing are twofold. You need to provide two things. You provide a graphical model, like a set of descriptions. You describe the causal relationship between things in the real world without approximation. And then the other thing you provide is sort of your desiderata. What do you actually want? What you wish the world looked like? And then we're going to be able to ask the question, how much does the real world differ from the thing that you want? And turn that into a sort of trackable objective that we can optimize. So let's actually try and do that, like an instance of that. So here are two diagrams, one pair of two diagrams that I argue explains representation learning as we do it today in machine learning. The thing on the left is sort of like a true description of what we do when we do machine learning for representation learning. And the thing on the right is that same diagram before, sort of what we want. And let's kind of dive in. So first we need to describe the real state of the world, sort of without approximation. And for that, we're going to kind of start as before, but I'm not going to pose like there is data, there are images and labels, but I'm not going to pretend that I know where they came from. I don't know the distribution that they came from. Instead, I just pretend that I can draw samples from the distribution, whatever it is. The universe makes that data. Now, if Alice is interested in building a machine, doing machine learning, and she can't impose her will on the distribution, what can she do, right? You can't change the real world. Alice isn't that powerful. But what she can do is she can augment the real world. She can build a machine. She can build a new thing. She can build a representation of the data. So she's going to try to design a machine that, like, let's say, eats an image and spits out some representation, just like a whole bunch of numbers, something that might be useful for some downstream tasks, right? She can try to do search or recommendations or something. She's going to build a machine, but she doesn't have to lie about that, right? That machine is a thing that she designs. If it has knobs, she can control those knobs, and there's no sort of approximation there. This is the kind of foundation of the information bottleneck method. And one thing I've always liked about the information bottleneck method, as opposed to something like maximum likelihood, is that it doesn't impose its will in this way. It doesn't assume that it knows the true distribution of the data. It only describes augmentations to the real world. However, as great as the information bottleneck is, I think it is missing some of the ingredients of what goes into doing this kind of thing today, as opposed to, I guess, now 20 years ago. And so let's keep going. Let's keep augmenting this diagram a little bit. The first thing I want to do is this is sort of like a technical thing, bootkipping, but I want to be honest. I'm not going to assume that the data is independent and like IID, independent and identically distributed. Instead, I am willing to say or approximate that the data is exchangeable. Like if you give me a data set and you shuffle it, I can't tell the difference. Now, De Finiti's theorem tells me that if I have data that is exchangeable, I can assume that there does exist some latent variable, something that if you knew, the data could be treated as it was independent only if you knew that thing. You should think of this as just like the universe. If you actually knew everything about the universe, if you actually knew the true data generating procedure, then you could imagine that the data was sort of independent. And I just want to like encode that and be honest about that in our description of the real world. The next thing is, if I'm doing this today, neural networks, I'm going to use something like a neural network. I'm going to use a parametric representation of data, and that, I'm going to build a machine with 1 billion knobs, and there's going to be a procedure by which I set those knobs, right? I'm going to do something like learning algorithm, and that learning algorithm is actually going to look at data. So I have to be honest about that. My learning algorithm is a process that looks at the first n samples of a data set and sets a distribution over all the knobs, the theta, the parameters of my parametric representation. And so I argue this is a graphical model. Really, it's just encoding the sort of causal relationships instead of conditional independencies between these 5 random variables that exist in the problem of representation learning, sort of as it happens today, sort of without approximation, without imposing our will. To emphasize, like all the stuff in red, the universe fixed. I don't get to control outside of my control. That's just a thing that's handed to me. What Alice builds is the stuff in blue. She decides on a learning algorithm that is a process for setting the values of parameters, as well as a parametric representation of data. Those are the things she designs. And now, what we want is a principle to guide her search. In the space of all possible learning algorithms and all possible representations, how does she choose between them? How does she decide which is best? And so to do that, we're going to phrase this as an extremal problem, as an optimization problem with regard to some target generative model. And for that, we need to specify another graphical model. I mean, the ones before. Like, what does the Bayesian do? The Bayesian wishes this is the way the world works. The Bayesian wishes that after Alice builds her machine, the thing that comes out of her machine is actually a true latent description of the world, right? Alice would love it if, she sticks an image into her neural network and out comes out, oh, this is a picture of Garfield. Because once you know that this is a picture of Garfield, you can both draw its picture and know that it's a cat. This is what you wish were true. And you wish that there was some latent variable Z that had all the information that you would need to reconstruct X and Y independent of each other. Also, since we get to design it, like if it was up to us, our description would be the correct one. It would be independent of the rest of the state of the universe, right? We don't have to depend on anything outside of our little model if we had the true model. Furthermore, we can choose, like, let's not marginalize over the parameters. Let's assume that there's only a fixed setting. We know exactly what they are. So how do we take that? We've got our 2 graphical models. We've got the thing on the left, which I argue is a description of what happens in representation learning. We got the thing on the right, which I argue is what you might want. And for this particular set of diagrams, how do we turn, or for any set of diagrams, how do we turn that into an objective? And what we're going to try to do is we're going to try to ask, like, how far away is the thing on the left from anything consistent with the right? How far away is the thing from the right, the real world, from the world that we desire? And sort of mathematically, we can phrase that as, what is the minimum possible KL divergence, divergence between the real world and any possible world consistent with our desires? Now, this seems like a horribly abstract, horribly intractable, horribly impossible problem to answer. But the calculus, the answer is that you can turn a crank, multivariate information bottleneck, Sloan's thesis, kind of predicators, and you can render that horribly abstract thing into a finite number of mutual information terms. You can characterize the degree to which the real world differs from the world of your desires as just a small collection of mutual informations. In this case, for those two particular diagrams, there's 6. The top two, completely outside of our control, they depend on the complexity of the underlying data generating process. There is something the universe provides that gives rise to data, and depending on how complex that is, I might never be able to hit my desires exactly, but that's also outside of my control. The thing that Alice gets to decide, the learning algorithm and the parametric representation, is going to suggest these other 4 terms. And so now, in the space of all possible things Alice could do, we can characterize the degree to which it mismatches with her desires by just tracking these 4 numbers. And that's, just like in the sort of the thermodynamic case, these are playing the role of our extensive variables, our state functions, the things that characterize the difference between different sort of Pareto optimal things. Now, only problem is mutual informations are intractable. We can't measure these things, but fortunately there are tractable variational bounds that we can achieve for each of these, and I'll try to talk about them in kind. So now, these 4 quantities are actually tractable things that Alice could compute that characterize the sort of space of all possible things she could do. First is the rate. This is a variational upper bound on the mutual information between z and x and theta jointly. What does that actually mean? That means if Alice builds her machine, she eats an image, she spits out some representation, and if she wanted to communicate that to Bob, the rate is how many bits it takes for her, it's the cost of sending that message. It's how much she has compressed the image. And of course, that's going to be relevant for the degree to which she's captured the relationships between variables. So this is the cost of the compression that she's achieved. Next is the classification error, variational lower bound of mutual information z and y. This is if she eats the image, spits out the representation, how well can she predict the label just from her representation, not from the image? And this is going to measure her ability to do sort of supervised learning, her ability to predict labels in the image. Next is the distortion, similar but different. Once she encodes the image, how well can she get the image back? How well can she go from her representation back to image space? This is the distortion. It's a measure of her sort of unsupervised performance. And lastly, there's a term I'm calling entropy. It's a variational upper bound of the mutual information between the parameters in the data set. The learning algorithm kind of eats or extracts a certain number of bits from the data set, and that's what this entropy captures. It's how, particular, how sensitive the learning algorithm is to the data set itself. And so now, Alice, she, given any set of distributions, she can compute these 4 quantities, and just like in the thermodynamic case, any set of learning algorithm and choice of any choice of learning algorithm and parametric representation will be a single point in the 4-dimensional space. If she considers all possible things she could do, that will trace out a 4 volume. That 4 volume will have a 3 surface, and that 3 surface are optimal. They're sort of the most extreme, the best that she could ever possibly do. All the things on the surface are characterized as the things that she can do that are most consistent with her set of desires. Now, I can't tell Alice where she should live on that surface, but I can certainly tell her that she should live on that surface because the surface are the sort of extreme state. And this is sort of how we get exactly our analogy with thermodynamics. To give you some kind of picture of what that looks like, I can't draw the 4-dimensional space and 3-dimensional surface, but if you kind of take a slice of it, there will be some boundary, and Alice should want to live on the boundary. Can't tell her where. That's going to depend on her downstream task, but she should want to live there, somewhere around there. So how does she move around on the surface? How can she explore this 3-dimensional surface? Well, she could just do sort of a Lagrange multiplier thing. If these are the 4 functionals that govern where she lives, if she chooses like any 3 coefficients, as she adjusts those 3 coefficients and minimizes its objective, she'll hit 8 points on that 3-dimensional bounding surface. And I mean that was a lot, right? I just went through a whole bunch. I probably lost most of you, but now I just want to tell you that if, in so much as what I said is true, now this objective actually encompasses a wide array of existing machine learning objectives today. Because if all you do is you kind of set all the coefficients at 0 and you try to find one corner of this surface, one corner of this three-dimensional surface where all you do is minimize C, that's equivalent to like ordinary supervised learning. That's just training a classifier, telling the difference between cat and dog. If what you do is do C plus rho R and you shoot a one-dimensional contour, not just a surface, one-dimensional edge, this is actually our paper from a few years ago, variational information bottleneck, sort of stochastic classifier that is better robustness properties. If all you do is minimize distortion, this is an autoencoder. If you've heard of those, you try to go from images to latent images. If you just do D plus R with coefficient 1, this is a VAE, if you've heard of that, the variational autoencoder. That's all it is. It's another corner, special corner of the surface. If you allow yourself a one-dimensional edge, you get a beta VAE, or a paper of ours, fixing broken elbow. It's sort of an information theoretic way of trying to do unsupervised learning. If you do these three terms, just one and another one-dimensional subsurface, the semi-supervised BA18 Metal 2014. Move over to the other side. If you do C plus S, coefficient 1, you get a Bayesian neural net, phased by backprop, or neural processes if you want to get the version of it. My colleagues at DeepMind. And if you allow yourself a one thing there, you get the information bottleneck grunge of Keeling and Swato. So if all of those different papers, are interesting and useful for doing different kinds of representation learning, and they're all lower dimensional subsurfaces of the three-dimensional surface, I guess the real question, the real kind of motivation of this work is, now that we have a unified description of all this, what if we kind of, actually characterize the entire surface, right? Just like there was in thermodynamics, are there useful properties that I could compute? Are there useful susceptibilities? Are there useful derivatives that I could evaluate that can help me tell the difference between different classes of learning algorithms, different optimization procedures, or even different families of parametric distribution? Just like in kind of physics, I can say, oh, metals are different from wood because they have much higher thermal conductivity. Could I say, oh, neural networks generalize better than random forests because they have a very high, DD, DR, DC? That's kind of the big question, the one that I kind of want to leave with you all is, hopefully this is a kind of a new way to think about machine learning that you haven't thought about before. So more similar to things you do appreciate, and it's really, yeah, that's what I'm selling. I'm selling a story, but I think it's sort of an interesting one. So at that point, so just like I motivated at the beginning, the thing is completely analogous to thermodynamics. You can imagine trying to compute some of these derivatives or susceptibilities. You can look at for things like phase transitions. Colleagues at DeepMind can identify kinks on the surface that have divergent second derivatives. These correspond to kind of semantically meaningful phase transitions in learning. You could write down generalized Boltzmann distributions, talk about all kinds of stuff that I don't get to talk about. In many ways, like, this is what I've been doing. My career has just been studying kind of subsurfaces of this space. Here are some various papers looking at various one-dimensional subspaces. And then more recently, I've been trying to look at sort of other corners of the space. I've lost some of the other slides, but there's been, yeah, okay. So let me just summarize again. So what was I trying to tell you? I think that there is a simple way, there is a general calculus, a general mechanism by which you can take two graphical models, turn a little crank, turn it into an information theoretic objective, which is like the sort of action principle. One instance of this program motivates most of existing representation learning, and I'm very excited that in the future we'll be able to use this kind of language to better understand why these things work as well as they do and make them all work a lot better. So I think I will stop there. I don't know what else is next.
All right, Alex, thank you for a very nice talk. Let's see, do we have questions from the audience? We can either try to look, okay, so Ji Yue, let me see if we can find you. We have 165 attendees, but let's see if we can make your mic available. And so you can ask your question directly. Okay, I
Yeah,
think
so
somebody has
I
just
also
enabled you.
apologize for the. I'm sorry.
Oh, go ahead. Ask your question.
So I think that was me talking. I don't know. I haven't heard anyone else.
I think that there are a few GWA accounts, and so I think Jay or somebody is trying to figure out which one to unmute.
Okay. Yeah. So I guess while we wait, I do apologize for the technical difficulties. I realized people couldn't see me. It probably wasn't the best. No, the audio quality is great, but had some difficulty setting things up. Hope it was still somewhat understandable.
So Jue, I'll try and read the question for you while we try and figure out how to unmute you. So there's a question about on slide 60, what is the physical meaning of rho, delta, gamma, and sigma? Is there one, or are they just constants to be altered?
Yeah, so they play the role. I mean, if you wanted to draw an analogy with thermodynamics, they are like they're like pressure, temperature, chemical potential. They're the first derivatives of the surface with respect to the functional. So they're like the intensive properties. I don't think they have as kind of salient a semantic meaning in the kind of machine learning sense as they do in physics, right? In physics, I can expose a cup to the atmosphere and set it at constant pressure. For a machine learning system, optimizing it at constant pressure or constant delta just means doing an optimization with a certain knobs to a certain number. But that is the analogy. They're like the intensive quantities, they're like pressure, temperature, chemical potential.
Okay, thank you. And John Visalta had a follow-up question. John, I've just unmuted you if you wanted to ask your question.
Okay, does my sound work?
Perfect.
Yes.
Okay. Great talk. Thank you for it. Regarding your four-term objective function that you just talked a lot about, is this the most general kind of objective possible? And if so, can you show that mathematically? And if not, what else can you imagine?
Yeah, so there is the kind of calculus that gave rise to this objective, the input is just kind of two graphical models. So any choice of two graphical models will give you a different objective. Now, I don't think it's the most general in the sense that you can certainly imagine building, Alice can build other machines, right? Instead of having a local representation, she can have a local and global representation, she can have hierarchical representations, and all of those will lead to more generalized versions of this kind of objective. I think the particular choice of diagrams that I focused on are interesting because they're sort of like the Drosophila megalanaster of machine learning in the sense that I think they have all the ingredients to make them interesting, and they're kind of the simplest that are, still interesting. If that answers your question.
Yeah, definitely. Thank you so much.
Yeah.
We also have a question from Deepak. So Deepak, I'm trying to find you so that I can unmute you. One moment, I think I just found you. Okay, so Deepak, your question about neural nets?
Right. So when I think of thermodynamics, right, I think of heat engines, right? So a heat engine takes in some energy and it does some work and then releases some waste heat at some certain temperature.
Yes.
So is there a sense in which you can think of a neural network as corresponding to an engine?
Yeah, so I think that's a fantastic question.
Yeah.
So there's kind of two parts. So first, the kind of optimization that we normally do in machine learning. So part of the difficulty versus physics, right? In physics, if I just like leave my coffee cup in the corner, it will reach equilibrium. Like the universe does that for me. For my neural network in the machine, like if I just sit there and do nothing, nothing will change. So the optimization that we're used to, where we like optimize the network, that's like us enacting the equilibration procedure. It's trying to move from the bulk to the surface. But once you're on the surface, in so much as they're a surface, you could imagine processes that move around on that surface, right? Isochoric processes, isobaric processes. In this case, it would be things like isodistortion surface contours or isoclassification contours. And actually, colleagues at so like Pratyush Tiwari has a paper, and I apologize, I originally had a reference in the slides, but I've lost it in this version. They have a paper that just came out recently where they extend this work and they actually realize an isoclassification contour on this surface, where they can take a neural network that's trained on MNIST, and without changing its classification accuracy, they can like swap out the data set from MNIST to CFAR10 by following like what would be the analogous thing to an adiabatic process, on the surface. So I think that there's a huge potential there for kind of trying to come up with algorithms that realize things analogous to isochoric, isobaric processes of like a heat engine, if that addresses the question.
Can I just ask a follow-up?
Yeah, sure.
Let's see, maybe we should be fair though, to just, we have a number of other questions. But
Sure.
you can follow up by email. So let me find another question as more are coming in. Let's see, I will go to Hadi. Let me find you, Hadi. Okay, so I'm trying to unmute you. One sec. Okay, I can't seem to unmute Hadi Bafai, but I'll ask their question, which is, recently there has been a surge of papers on representation learning using mutual information maximization. For instance, this mutual information can be between my data point now and some latent representation of data in the future. I was wondering, where does this kind of approach fit in the framework described here?
Yeah, so that's a good question. So there's been a ton of work about information maximization for representation learning. Now that doesn't sort of directly fit into this framework. I mean, that's certainly work that I follow. I think it's interesting. We have our own papers kind of discussing some of the issues with those objectives. I do think that they are kind of somewhat distinct from what I talked about right here. Yeah, it's a different objective. I don't know if, yeah, it's a different objective. I do think that work is interesting. I do think that's
okay, so let's see. Let me move on to Harrison. Thank you. So Harrison, I'm trying to unmute you. It seems that in some cases that it is not easy to unmute a person, so I guess some people are actively muting themselves. So Harrison Proper asked, from this new view, can you already see hints of new machine learning models or algorithms, that is, gaps in current practice? Also, given the insight that one imagines a single geometrical object describes in many ways, would it be possible to use coordinate independent methods to explore this object?
Yeah, I think those are great questions. So in terms of sort of missing corners, yes, I think it's sort of, I kind of walked through some existing papers that explore the surface. There are, very naturally, I mean, just the sort of like the generalization would allow you to, I expect the whole is better than the sum of its parts, in the sense that I think there are very useful models of that don't restrict their attention to just a one-dimensional like edge of the surface. And I think that's already borne itself out in practice. Like a semi-supervised VAE can do things that a VAE can't. And so this general object, which would be like a, I don't know, Bayesian semi-supervised VAE or something, could do things that we might not have seen before. I also think the question about a better sort of geometric understanding of the surface and motion on the surface is a good one. And I think that that is also some of the ideas that motivate the work that I tried to hint at by Pratyush Tiwari, where they actually, work out what it would mean to follow something like an isoclassification on the surface that involves kind of being more cognizant of the differential geometry on the surface. And so I think there's a lot of work to be done there to kind of like answer this question.
Hello. So let's see, Kevin. I skipped your question. I'm sorry about that.
Oh yeah, and I
Thank you.
don't want to run into time for the other speakers if we going late.
Okay,
Or
so
whatever.
I think that this will be our last question. So I think we're doing okay in terms of time, and so we'll let Kevin ask his question, and then we'll move on.
Great, thanks. Really cool talk. So I'm trying to take my experience simulating molecular systems to understand how we calculate these things. So usually free energies and susceptibilities, derivatives, they can be difficult to calculate. Can you briefly talk about what makes sampling the probability distribution feasible in trying to calculate these analogs?
Yeah. So yeah, because of time, I wasn't able to go into much of the sort of technical details of how we actually calculate these quantities, but they are ultimately they are variational bounds. They are variational bounds. So in order to calculate the rate, it requires its own sort of optimization problem. That is one that we kind of do these days, right? So you should think of it as analogous to, if you wanted to compute the free energy of the system, one thing you could try to do is like Feynman-Bogoliagov. You could do variational, you could compute a variational bound on the free energy. That's what we're doing here. That's the technology that we're utilizing in order to try to estimate these quantities.
I see.
And it does require kind of building other neural networks and optimizing those in order to evaluate the quantities. But that's something that's sort of we can do, right? So.
Really cool. Thank you.
Yeah.
All right. So thank you so much. So we're going to have to move on. I'm going to ask Alex if you have time to respond to some of the questions that weren't answered in the chat. Then we'll move on to Nicole. And so Nicole, I'm going to make you the presenter. I'm going to drop out with my webcam, and I am going to just give a brief introduction. So Nicole Yunger Halpern is an ITAMP postdoctoral fellow at Harvard. She earned her PhD at Caltech, winning the International Ilya Prigogine Prize for a thermodynamic thesis. She re-envisions 19th century thermodynamics for the 21st century using the mathematical toolkit of quantum information theory. She calls this research quantum steampunk, after the steampunk genre of art and literature that juxtaposes Victorian settings with futuristic technologies. So I just had to love the word quantum steampunk. Without further ado, here's Nicole. I'll drop back in 30 minutes to let you know that it's time for additional questions and answers. All right, Nicole, looking forward to this.
Great. Thanks very much for the introduction. I should add that unfortunately today I'm not talking about anything quantum, but hopefully it's up next. And so let me share my presentation. There we go. I'd also like to thank the organizers for the invitation to talk here. It's great to connect with this new audience. I don't usually interact with a GDS topical group, but it's great to get to know you. And thanks to everybody for coming to this webinar from all around. Over the past few months, we have been pushed pretty far from our equilibria, and we've learned quite a lot in the process. First, we have learned about a new friend on the block. We've learned how to, for example, give seminars online. We've learned how to repurpose household items, and we have learned that our next door neighbors are really, really, really bad at playing piano. It is pretty amazing how much we can learn when pushed far from our equilibria. And not only us, but also very simple many particle systems. Here's one physical example of a system that learns about the drive that pushes it far from equilibrium. First, I'm going to give you a sketch of the story, then later on I'll give you the details about Hamiltonians and so on. But imagine a classical spin glass that interacts with a heat bath. Suppose that we impose some magnetic field A on the system. That you can imagine it as pointing along the z direction. And from now on, I'm going to omit the arrows over vectors. The spins will gain energy from the field, absorbing work. And then they will flip, dissipating heat to the heat bath. Suppose that we create a drive. I'll define a drive as a set of fields, for example, A, B, and C. Suppose that we randomly pick a field from the drive, apply that for a while, randomly pick a field again, apply that for a while, and repeat those two steps many times. You can think of this process as training the spin glass on this drive. what happens to the power absorbed by the spin glass? At first, it's going to be quite high, and then it will tail off. Now suppose that after that process, we apply a new drive to the spin glass. The absorbed power will again spike and then tail off. Now suppose that we go back to applying the old drive. The absorbed power will spike, but it spikes less than before. The spin glass has this way of signaling that it recognizes the original drive. It has learned the pattern of that drive. What seems to be happening physically is it finds some corner of configuration space in which it doesn't get knocked around very much by the drive, so it doesn't absorb a lot of power. This is just one example, but there are many body systems that learn the drives that push them far from equilibrium. There are all sorts of examples: polymers, rafts of soap bubbles, non-Brownian suspensions, even crumpled sheets of paper. And these behaviors hold promise for building memories and otherwise engineering materials. Work on this has included theoretical predictions and experimental observations. And if you're interested in these behaviors, I strongly suggest this review. Frankly, it was one of the most inspiring papers that I read last year. This learning behavior has been detected with thermodynamic signatures. I just told you a story about how absorbed power can be used to detect such a behavior. Polymers exhibit strain that can signal this learning, and so on, which is nice, but thermodynamics was developed a long time ago for a very different purpose than detecting learning of strong drives by many-body systems. In contrast, over the past few days, we've learned from computer science quite a bit about learning. So why don't we use machine learning to learn about the learning by many-body systems of the strong drives on them? That was the mission of this paper, which I wrote with collaborators from MIT, Weishan Zhang, Jacob Gold, Sarah Marzan, and Jeremy England. We identified a parallel between representation learning, which we heard about from Alex, and certain problems in non-equilibrium statistical mechanics. Then we used this parallel to detect and to measure this many-body learning more precisely and more thoroughly than the absorbed power, this thermodynamic measure. Here's where I want to go in the rest of the talk. First, I'll introduce representation learning. Then I'll introduce the parallel between representation learning and statistical mechanics. Then I'll give you more detail about the physical system with which we illustrate our toolkit, the spin glass. Then I'll show you what neural network we used that we applied to the spin glass in order to detect its learning. I'll show you how to use this toolkit in order to use our neural network in order to detect classification of drives by the spin glass. This is just an example. You can also use our toolkit to measure memory capacity, discriminatory ability, and the detection of novelty. Then I'll talk about the opportunities opened up by this work. First, let's review representation learning. The representation learning is a branch of machine learning. Here's the structure of a neural network that undergoes representation learning. The neural network gets some high dimensional variable X, for example, a sentence with a word missing, for example, the blank is shining. Then the neural network compresses this variable into a smaller latent variable, Z, that's much lower dimensional, which might be word types and relationships. Then the neural network decompresses Z into a prediction Y of a high dimensional variable Y hat. Y hat could be the empty word missing from the sentence, and the prediction could be sun. During the compression process, there is a trade-off. The neural network wants to compress enough information that it can predict correctly, but it wants to compress only enough information to save space. So some parallels between machine learning and statistical mechanics, of course, have been known for many decades. Representation learning, as far as I know, has been compared to statistical mechanics less. We heard a great example of a comparison from Alex just a few minutes ago, which he compared representation learning with thermodynamics and the framework that we learn in undergrad and grad school. I'm more interested in parallel with far from equilibrium statistical mechanics, although you could make a similar argument, I suppose, about equilibrium systems. So here's the structure of some problems in statistical mechanics. We have a system that is in some microstates. microstate you can think of as a very high dimensional variable because there are many different particles. They can have many different positions and momenta. So this microstate is a lot like the X received by the neural network. We tend to compress that microstate information into a macrostate, for example, an energy, a number of particles, and so on. And that macrostate should reflect what this system is experiencing. In a sort of extreme example, suppose that our system is a collection of particles in a warm pond. If the macrostate is sludge, then there might have been certain drives on the system. If the macrostate of the system is a number of microorganisms, then maybe at some point in the past there has been lightning striking the pond. So this macrostate is this compressed description, a lot like the latent variable Z, and from the macrostate we might predict about the drive that's been acting on the system. That drive prediction is like Y for the neural network. We want to use this parallel between representation learning and the statistical mechanical problem in order to detect and measure learning by statistical mechanical systems of the strong drives on them. I'm going to illustrate how we can do that using a model of a spin glass. That's going to be our toy example physical system. Consider a spin glass of 256 classical spins. Each points upward or downward, as represented by a spin variable plus or minus 1. You can think of the spins as pointing along the z direction. Spin j experiences a Hamiltonian h of t that changes with the time t. It has two terms. The first term is the interaction energy. These couplings j sub jk form an Erdős-Renyi random network. So each two spins, j and k, have some probability of interacting. We've set the probability so that each spin couples to 8 others on average. Once we figure out which big j's are non-zero, we select their values according to a standard normal distribution. The second term in the Hamiltonian is the field energy. This a sub j of t represents the magnetic field experienced by the jth spin at time t. You can think of that field as pointing along the z-axis as well. Suppose that you take the value of the field at time t for all of the spins j. I'm going to package that up into the very simple notation that is simply A. So A represents the entire field across the whole spin glass. Our spin glass is going to exchange heat with a heat bath. First of all, I'm going to set Boltzmann's constant to 1. But what controls the thermalization rate are two parameters. First, the temperature of the heat bath, T, 1 over beta, and an energy barrier. So this is the barrier that spin glass has to hop over in order for a spin to flip. So the rate at which spin j tends to flip is given by this equation here. It has the form of the Arrhenius law, and it obeys detailed balance. So it checks out against our expectations about what thermalization processes tend to involve. And the numbers are such that the spins tend to have energy to flip only when driven, so they don't flip very much. Earlier, we saw that we could detect learning of this many-body system, of this drive on it, by monitoring the absorbed power. In order to talk about power, I have to define work. We'll define the work as the change in the spin glass's energy when the field changes. So suppose that the field changes from a j of t to a prime j of t. The work equals the sum of the change in the field times the spin variable for all the spins. I'll call the power the work over 100 seconds because 100 seconds is how long we apply a field for at once. Here's what we're going to do to the spin glass. First, we'll initialize the spins in random configuration C. Then we'll let them relax in the absence of the field for 100,000 seconds. At the end of this time, the spin glass ends up near some local energy minimum. Then we'll drive with a field for 100 seconds. We'll drive with the next field for 100 seconds and keep on this driving process. This is the training of the spin glass. And the last step, the last driving of the spin glass is testing. If we need to repeat this protocol in order to gather statistics, we will begin each trial with the same configuration. This spin glass in a certain parameter regime can learn the drive well, even according to the absorbed power. This regime was found in an earlier paper, and it corresponds to these two values of the parameters. These are just numbers. What do they mean physically? The temperature is high enough and the barriers are low enough that the spin glass can explore phase space and find a nice corner of configuration space. But the temperature is low enough and the barriers are high enough that the spin glass is not hopelessly always wandering around. Once it finds a good corner of configuration space, it can lodge there. What neural network do we use in order to analyze this spin glass and detect its learning of the drive on it? We use a variational autoencoder, which was mentioned by Alex. As he mentioned, this is a generative model. So the network receives samples little x of a variable big X. It learns about the distribution from which x is sampled, and then it generates new samples from its approximation to that distribution. We are going to feed into our neural network configurations x of the spin glass, and our neural network is going to output configurations. You might protest, if you've been paying close attention, that this model differs from the story I told when I talked about a parallel between bottleneck neural networks and representation learning. When I was talking about that parallel, I put a configuration down here and a prediction of a drive up here in place of y. So we could use such a neural network in order to analyze our spin glass. That's possible. But as far as we were aware, the state of the art would require us, when using that neural network, to have the neural network perform supervised learning. So the neural network would receive during training not only configurations, but also the labels of the drives that produce those configurations. The labels of the drives form information not directly available to the spin glass. So if the neural network received that extra information and the neural network did its job well, it predicted accurately, we could not attribute that accuracy just to the spin glasses doing a good job of learning the drive on it. That could be just the extra information that we gave the neural network. So we wanted to make sure that the neural network would perform unsupervised learning. That's why we use this structure, which does perform unsupervised learning. So the network approximates the distribution using Bayesian variational inference. And our neural network has 5 fully connected hidden layers. We have the input layer, then a layer of 200 neurons, another layer of 200 neurons. Our latent space consists of just 2 neurons, which we'll call Z1 and Z2, then 200 neurons, another 200 neurons, and our output layer. We can visualize the 2-dimensional latent space like this. Let's draw along the x-axis the first latent dimension. So this represents 1 neuron, or a continuous valued real number. Along the y-axis, we will draw the second neuron. Now, how did we produce the plot that I'm about to show? We took our spin glass, we formed a drive from 3 fields, A, B, and C, and then we drove the spin glass with this drive by applying 1 field and then selecting a field at random and applying it, then selecting a field at random and applying it, and so on. Then we took the final configuration. We did this in a lot of trials, and we took those final configurations, we trained the neural network on them, and the neural network populated the latent space like this. I have artificially colored the plots, or actually my co-author Wei-Shen has artificially colored the plot so that the dots that were produced by configurations that were produced ultimately by the same field have the same color. We can see that the neural network has clustered dots associated, or dots of the same color, which correspond to configurations generated by the same field together. That means that the spin glass has learned the drive on it. And so the drive has really imprinted itself on these configurations. Let us use this latent space in order to learn about what the spin glass itself has learned about the drive on it. I'm going to show as an illustration how we can use this toolkit to measure classification. First, what is classification? So classification involves identifying a stimulus as belonging to one of many possible categories. Here's what we'll do. We'll run a protocol on the spin glass. Then we'll use the variational autoencoder to quantify the spin glass's classification ability. Then we'll do this by analyzing the latent space. Then we'll use the absorbed power to quantify the spin glass's classification ability. We'll find that the variational autoencoder detects more of the classification ability than the absorbed power does. Here's what we're going to do to the spin glass. First, we'll generate some random fields, A, B, C, D, and E. From 4 of those fields, we'll form a drive D1. We'll train the spin glass on this drive in each of 1,000 trials. Then from another 4 fields, we'll form the drive D2, A, B, C, and E. We will train the spin glass on this drive in another 1,000 trials. Then we'll keep repeating this process for each of the 5 possible 4-field drives. Then we'll take all of these trials, we'll randomly select 90% to train the variational autoencoder with, and we'll use the rest of the trials for testing. Here's how we use the variational autoencoder to measure the spin glass's ability to classify drives. Let's pick a time t, take the training trials, and identify the configurations occupied by the spin glass at time t. We will train the variational autoencoder on these configurations. Each configuration is mapped to a dot in latent space. Here is a picture of latent space. This particular picture was not produced by the spin glass protocol that I just described, but I just wanted to remind you what latent space can look like. So the dots form a probability distribution on latent space. Then we take a test trial, we find the configuration occupied by the spin glass at time t, and we input that into the variational autoencoder. The neural network will compress that configuration to a dot in latent space. Then we'll use that probability distribution to calculate which of the drives most likely, according to this distribution on latent space, produce that dot, that configuration. We used the maximum likelihood estimation method in order to do this. And then we test the variational autoencoder with each of the other test trials. The fraction of trials, test trials, in which the variational autoencoder guesses correctly, or we can guess correctly which drive produced the configuration using the variational autoencoder's latent space, is called the score. And we can plot the score against the time at which we took the configuration. The score looks like this. Along the x-axis, we have the time for which the spin glass trained, and along the y-axis, we have the score. The upper bound is 1. This is the score if we always predict the drive correctly. There is a lower bound of 0.2 or 1/5. This is the score that we would get if we just randomly guessed which of the 5 drives produced a given configuration. You will notice a little bit of a gap between this lower bound and the beginning guess of our variational autoencoder, which doesn't make a whole lot of sense, you might think, because at time 0, the variational autoencoder has basically no information about the drive because the spin glass has no information about the drive. And the variational autoencoder gets information only from the spin glass. We think that that little gap is just an artifact of stochasticity of 3 types. There's stochasticity in the initial conditions of our spin glass. Maximum likelihood involves stochasticity, and so does stochastic gradient descent during learning. After a short time, the score rises and comes to oscillate a little bit under 1. So the spin glass learns to classify drives quite well, according to the variational autoencoder. What classification ability does the absorbed power attribute to the spin glass? We'll analyze that as follows. Let's take the training data, that 90% of the trials of our spin glass. Let's pick a time t. Let's pick a drive d sub j. We'll identify the power absorbed while that drive was applied at that time. We'll take all of those instances of absorbed power and form a histogram from them. We'll repeat this process for every drive d sub j and every time t. So we end up with a whole lot of histograms. Then we'll take a trial from testing. We will identify the power that was absorbed at a time t, and we'll use the histograms to guess which drive most likely produced this amount of power. Then we will guess for each of the other test trials. The fraction of the trials in which we guess correctly forms the absorbed power score, which looks like this. This yellow line at the bottom. So the score begins at the random guessing score, and it rises to oscillate around 0.25. So according to the absorbed power, the spin glass does learn to classify drives, but it doesn't learn very, very, very well. The variational autoencoder picks up on a lot more of the spin glass's ability to classify drives. So in summary, suppose you have a many-body system that can learn the drives that push it far from equilibrium, and you're wondering, how do I quantify the classification ability of my system? You can use the score of maximum likelihood estimates calculated from the latent space of a variational autoencoder. So I showed you how to use our toolkits, an example of quantifying classification, but there are other features of learning that you can quantify with our neural network method. We saw classification, which involves the question, which drive is this? You can quantify the memory capacity of your system. Memory capacity involves the question, how many drives can the system remember? Discrimination involves figuring out whether a given field is made up of fields seen before. And novelty detection requires the system to answer the question, has it seen a given stimulus before? So, a lot of opportunities are opened up by this work. First, there's the possibility of identifying new macroscopic variables for strongly driven statistical mechanics. We physicists and chemists who are trained in statistical mechanics classes tend to go to the usual thermodynamic variables when we do statistical mechanics. Neural networks don't have the bias of decades and decades of statistical mechanics classes that we have. So the neural network might pick up on better macroscopic variables to use to characterize a system. And so we looked at our latent space, which has, again, 2 dimensions. And we were wondering, do these 2 dimensions correspond to some of the usual thermodynamic variables that would come to our mind, like absorbed power and magnetization? The answer is no. It seems that the neural network might be picking up on new thermodynamic type variables or maybe combinations of familiar variables. So decoding latent space into physical characteristics that we can measure and maybe use as better macroscopic characteristics in statistical mechanics is one opportunity. And I can say more about this. I figured I probably wouldn't have time during the presentation, so please feel free to ask more about this during the question and answer session. I think it is an exciting opportunity and one that we'd be interested in getting input about. Also, this toolkit looks well suited to solving outstanding problems in many-body learning. For example, this is an image of a raft of soap bubbles. So these dark brown dots are soap bubbles. This is one system that recently was shown to exhibit many-body learning of strong drives. This is another system. It's a system of grains. Each grain has a hole in it so that you are able to see its orientation. This is a system that can learn the amplitude of a force that compresses the system. There are a number of questions about these systems that have been shown by thermodynamic measures to learn the strong drives on them. For example, what distinguishes the microstates of trained systems from the microstates of untrained systems? Or there are all sorts of things that you could measure in order to detect a learning. Which of these quantities is most important for detecting learning? And exactly how much learning does each degree of freedom encode? And there are other questions. So currently I'm working with these folks on applying our toolkits to their physical system. And if any of you has a favorite system of yours that exhibits this sort of many-body learning or memory, and you'd be interested in applying this toolkit to answer sort of more quantitative questions, then please feel free to reach out. I'd love to talk. And we propose that there is a parallel between representation learning and some problems in non-equilibrium statistical mechanics. We then used the representation learning neural network in order to learn about the statistical mechanical system and specifically quantify its learning behaviors. But we could go in the opposite direction because we know by now a fair amount analytically about non-equilibrium statistical mechanics, and there are some questions that remain about representation learning. For example, how exactly do variational autoencoders compress? So we might want to use this parallel together with what we know analytically and conceptually about statistical mechanics in order to learn about representation learning. In summary, we talked about representation learning, a particular model of machine learning. I proposed that there is a parallel between representation learning and certain problems in statistical mechanics. I introduced a spin glass as an example of a many-body physical system that learns the drives on it. I showed you a neural network that has a bottleneck, undergoes representation learning, that we can use to learn about the learning by the spin glass of the drive on it. I showed you how we can use this toolkit in order to quantify the classification ability of the spin glass. And we can also apply our toolkit to quantifying the learning behaviors or the facets of learning behaviors of memory capacity, discrimination, and novelty detection. And as I described, there's a lot more to be done. Thanks very much for your time.
Thank you for an excellent talk, Nicole. So we'll now open this up for questions. So I see that Conrad Cole has a question. So Conrad, I've unmuted you to ask your question.
Yes, hi. I meant to ask this question for the previous talk, but I think it should apply here as well. I'm curious about how these frameworks, whether or not they've been utilized and or applied to cluster expansion problems coupled with Monte Carlo simulations and the semi-grand canonical ensemble, for example. So in terms of solid state physics sort of problems.
This sounds like perhaps you're referring to a number of the, well, let's see. So Alex went through a number of machine learning models. Maybe you're asking about whether those tools have been applied to this particular class of problems. For my part, we were applying representation learning to some classical many-body system that exhibits memory or learning behaviors. So as far as I know, there's sort of a subfield of classical statistical mechanics that involves this memory or learning behavior. And as far as I know, it's been mainly studied through the lens of measuring thermodynamic signatures like absorbed power and stress and strain, together with sort of the usual data analysis. And we were introducing into that field representation learning. I would be interested in taking this representation learning toolkit and applying it to many other systems within this field of many-body statistical or of many-body learning. I'm not familiar with exactly what class of problems you have in mind, but our toolkit, one advantage of our toolkit is that it's somewhat general. For instance, in existing studies on this sort of memory behavior, some studies involve measuring the absorbed power, some studies involve measuring the strain. What you measure depends on the particular physical system. To use our toolkit, you just need to take the configurations. It doesn't matter very much what sort of a system you have. So this toolkit is fairly general. So it's possible that your class of problems would be amenable.
Okay, so let's move on to Megan. Megan, I've unmuted you so you can ask your question.
Oh, great. I actually had two. Can I do them one after the other, or do you want me to separate them?
Maybe just the most important one, just in the interest of fairness.
Okay, sure. It's kind of they're both kind of minor points. So I'm wondering, you're using this maximum likelihood estimator in the latent space. So does that mean you're essentially just not using the top part of the inverted triangle of the VAE?
Correct. Yeah,
Okay.
we have the VAE, well, the VAE creates the latent space while it's compressing in order to decompress. As I said before, our story about the parallel between representation learning and statistical mechanics problems would suggest that we have coming out the top predictions of the drive. But as far as we were aware, according to the state of the art, if we had a neural network predict the drive, then the neural network would have to undergo supervised learning, and that would create some conceptual problems. And that is why we had our neural network predict configurations, because such a neural network could undergo unsupervised learning. And from the neural network, we could infer about how well the spin glass was learning the drive on it. If there are advances that somehow we were unaware of, or if there are new developments such that we could get a neural network to do a good job of being able to take in configurations and predict drives while undergoing unsupervised learning, then that could open up some alternative analysis possibilities. So you could still analyze the latent space, but also you might be able to use the drive predictions.
Right. Okay. Thanks.
Okay, and we have, I'll skip ahead just a little bit to one question from John Visalta. So John, I've unmuted you so you can ask your question.
First of all, great talk. Really cool analogy, clearly presented. So my question is, what kind of obstacles do you think you might encounter, technical or otherwise, in trying to apply this framework to more complicated many-body systems? As far as I understand, spin glasses are nice and convenient because like the state space is easy to understand. It's clear what making a perturbation means because you can just flip an arrow and math is feasible.
Yeah, so at the moment, I'm, as I mentioned, working with another group on applying this to their physical system. One very immediate difference was that their system had an awful lot more particles. So just the resources required are greater. But there are some options for dealing with that. For example, if you're giving just a ton more information to the neural network, then you can expand the latent space to give it a bit more dimensionality, to give it some more power. We found that very often 2 dimensions sufficed. And you can visualize 2 dimensions easily, but you can also visualize 3 dimensions, and you can deal with 4 dimensions. Just what we thought. And we also, in different ways, challenged our neural network by feeding it a lot more information of different types. For example, we tried 50 different drives instead of just 3 or 5. We found that increasing the dimensionality of the latent space did help, but what was important was that the dimensionality of the latent space that we needed in order to separate out those dots into colored clumps was much, much less than the dimensionality of the whole many-body system. So still the compression was useful. We spent a little bit of our long paper talking about feasibility. So the link that I provided to the GDS is to our short paper. The short paper refers to a long paper, and in the discussion section of that, we talk about feasibility. For instance, could you expect to measure the microstate of a many-body system? We usually expect not to be able to, but there have been a number of recent experiments that have done a really amazing job on really measuring to pretty nice precision micro properties of the system, so that you could feed those microscopic configurations into a variational autoencoder.
Thank you.
All right, well, thank you very much. With this, we need to move on to our final speaker. So thank you again, Nicole, for an excellent talk. So we now turn to Pratyush. Nicole, I'll ask if you can answer some of the unanswered questions in the chat in a little bit. We'll give you the ability to do that shortly. So Pratyush is a professor at the University of Maryland, College Park. He has a joint position in the Department of Chemistry and Biochemistry, and the Institute for Physical Science and Technology. He's also affiliated with chemical physics and biophysics, and he received his PhD from Caltech, working with Axel van de Waal. And so we're looking forward to hearing from him today. So with that, Pratyush, if you'd like to start, I'm going to turn off my webcam. I'll turn it back on when you have 6 minutes left, which will be the question and answer period. And you can show your video if you would like to.
Sure. Can everyone hear me?
You're perfect.
Okay, great, perfect. So, all right. So thank you very much for this opportunity to come and present to you this work. I would have liked to speak in person, but this is what we have. So as it was mentioned, I'm an assistant professor at University of Maryland in College Park, not too far from Washington, DC. And I've been here a little under 3 years. And my lab, it's an interdisciplinary lab hosted in the Department of Chemistry and Biochemistry, but also in this very unique institute called IPST, which has, I would like to claim, which has been at the forefront of statistical mechanics for the last few decades. And in my lab, we like to study really complex systems so big that we have no right to be studying them, but they're very important. So any breakthrough we make, any progress we make could have enormous repercussions. For example, how do proteins interact with drugs? How do crystals nucleate and things like that? And I will tell you more about these problems. And the reason why I'm talking to this group today is because we use a variety of machine learning or AI-based architectures to study these problems, and we also try to improve upon them. These are some of the recent papers which we have published. You can also go to my Twitter or to my Scholar Google to get the more recent full list of publications. So my group is quite interdisciplinary. We have a couple of very hardworking undergrads, students from different departments, given the nature of our research, some collaborators, some alumni, and these days working from home. Honestly, it seems like my dog is my closest collaborator. He is well trained. He went to the dog obedience school nearby. So, and we get funding from a variety of sources and also supercomputer resources wherever we can get hold of them. So a big driving force for our research is to explore synergies between AI and statistical physics to develop next generation simulation methods. So in a live audience, I would have given this as a pop quiz. So these days I like to give a lot of pop quizzes because I've been teaching undergrads and I find them to be extremely useful, believe it or not. So this pop quiz, I would like you to take it. It's a take-home pop quiz, okay? So you have to answer it yourself and grade yourself. So this chapter, this book chapter snapshot says confronting the partition function. And I would like you to think whether it comes from Goodfellow and Yoshua Bengio's book on deep learning, or it comes from Mark Tuckerman's book on statistical mechanics. So partition function is a term we commonly encounter in StatMech. And if you look very closely, you will tend to think even more that it is from StatMech because it talks about things such as Jarzynski, who is a colleague at Maryland in my department. So when I give this in a live audience, trust me, typically I get 50-50 opinions. 50% of the people seem to think it comes from either of these books. The truth is it comes from deep learning. Look, it's online, deeplearningbook.org. So StatMech has confronted these partition functions for as long as StatMech has existed, which is around 120 years. We attribute it to Ludwig Boltzmann. Machine learning seems to be rediscovering the same problems, often discovering new tools to solve them, and often rediscovering that the tools that they have found to solve them were already well known to StatMech people 70, 80 years ago. And what my lab tends to do, likes to do, or is driven to do, is to explore these synergies. Try to use methods from deep learning in StatMech, methods from StatMech in deep learning, and apply it to very practical problems. So when I say simulation methods, I specifically mean something very simple today. It's something called molecular dynamics simulations. It's essentially solving Newton's law of motion. If you have a bunch of atoms that are talking to each other, and if you know what is the force through which they talk to each other, where did the mouse go? If you know the force through which, no, I would like my mouse to be here. All right. If you know the force through which atoms talk to each other, you could just solve force is equal to mass time acceleration. You could get acceleration by doing force divided by mass, and you could propagate the system as a function of time. So in principle, this is you can do it analytically if you had only 2 atoms, but the systems we are interested in don't have 2 atoms, they have typically a million of atoms. And even for 3 bodies, 3 atoms, it becomes a chaotic problem. Depending on the initial trajectory of the system, initial condition of the system, you can get very divergent solutions as you evolve the system. And more importantly, if you're solving for pairs of equations, for 4 systems, you can imagine that there are 6 pairs of interactions. As you go to n particles, you have on the order of n square interactions. Due to some clever tricks, you typically end up with n log n type scaling, but that's what you have. So you can solve Newton's law of motion for a given bunch of atoms starting from where they are. And this is kind of what the title of my talk meant. Just because you know F is equal to ma doesn't mean you know everything about the system. Dynamics that emerges as you increase length scales and as you go to different time scales is so rich and it's so different from what you would just expect from F is equal to ma. These things could be connected with harmonic springs, and that would lead to completely different dynamics. For example, it's a question I often give in my classes, a crystal made up of only harmonic springs never expands. As soon as you introduce a slight enharmonicity here, you can see thermal expansion. So there are wonderful properties that happen due to interacting behavior, and therefore we can predict in principle if we could solve Newton's law of motion. There is a big, and so what do we want to do with this? We want to solve very practical problems with solving this Newton's law of motion. One of the things that motivates us is figuring out how drugs work. So this over here is something called a kinase. If you haven't taken any degree in biochemistry, kind of like me, then you wouldn't know what's a kinase probably. But you know probably what's an ATP. So ATP is the energy currency of the body, right? So the kinase is the ATM card that you use to withdraw the ATP energy currency. So if a kinase goes rogue, it is implicated in a variety of diseases. In fact, after GPCRs, kinases are currently the #2 drug targets on the market. So when this particular drug, you can see it in red over here, imatinib, came out in 2001, it was called Wonder Drug of the Century. And I believe, apart from Viagra, this is the only drug which has made it to the cover of Time magazine because it was a superstar. People who were dying with death probability of around 90%, suddenly the rate dropped down to 20%. It was superstar. But 13 years later, the same drug was featured in the context of other drugs. And this is something, if you have had anyone, I hope not, experience cancer in your family, you would know this cancer comes back, right? It fights back. And the typical reason for that is mutation. So what this drug does is goes and blocks the kinase. But the kinase fights back. It undergoes little mutations, little defects here and there, which will make the drug ineffective. So my PhD is actually in material science, where also we deal with defects. The funny thing in material science, you never think about one defect at a time. You always think about a forest of defects. In biology, you can actually kind of make a lot of headway just by thinking of one defect at a time. Because if you have too many defects in the protein, then it won't be able to do what it wanted to do. So these point defects can be very effective. These are called resistance mutations, for example, and they can make the drug ineffective. So we would like to, so if you just saw the crystal structure of this protein, you wouldn't be able to tell why should this mutation have an impact on this drug out here, right? So we would like to use simulations in order to see how does the drug actually interact with the protein. What's, if you could just solve, in the end, as Feynman is attributed to saying, it's all about jingling of atoms, so how do these atoms jiggle? What is the mechanism through which these atoms are talking to these atoms? What's really going on? So we would like to study things like this. We would also like to study how do proteins change different forms. And proteins, like in the last picture, you might be led to think of protein as a static object. But in reality, it's highly flexible. And depending on small perturbations in the sequence space, the protein conformation space can undergo huge perturbations. And we are also interested in how to inhibit not just protein, but RNA targets. At this point, if you go like, too much biology, I don't care about RNAs, I must warn you that you should care about RNA, because the reason this webinar is happening online is because of an RNA target, namely coronavirus. So if you knew how to better inhibit RNA, then maybe this pandemic would have lasted a bit, let's not do that. So RNAs, for example, are desirable drug targets. If you could block them, you could even move towards personalized medicine. The problem is they're very, very flexible. So the protein flexibility that you saw in the last slide becomes even worse for RNA. And just by looking at an experiment, you can create a snapshot from an experiment. But that doesn't tell you much. So in fact, only less than 100 reported structures exist for RNA bound with synthetic ligands. But for protein, the number is on the order of 100,000 or more, at least 200,000. So this is a collaboration with National Cancer Institute, where we would like to develop methods to understand how to bind to RNA. But the common, and I'm not going to talk about all these problems today, but I want to give you a flavors. I'm mostly going to focus on methods for the remaining of the talk. I want you to remember that with these methods, we are trying to tackle the type of problems that I feel like if I spoke to my grandmother about it, she would be very happy that I'm trying to tackle these problems of immense societal relevance. So with Newton's law of motion, you have a time step of femtosecond. And if you solve it on a supercomputer, Deep Thought 2 is one of the computers at UMD campus, it's quite interesting that, so for every pair of atoms, once you solve Newton's law of motion, you evolve the clock by 1 femtosecond, maybe 2 femtoseconds. So once you solve on the order of n log n equations, which is a large number for a protein made up of 100,000 atoms in water, once you solve that many equations, so which is 10 to the power 5 squared, 10 to the power 10 equations in principle, you evolve your clock by 1 femtosecond. Yet on supercomputers, it's possible to reach on the order of microsecond in a couple of weeks, which is very impressive. And something happened recently. People realized that hardware that was being developed for keeping undergrads from getting bored, these GPUs where the blood is so real, you just can't take your eyes off the screen. So nothing wrong in keeping undergrads from getting bored, but people realized that maybe this hardware should be put to better use. And so GPUs were put to use for MD simulation, and they also put the boundary a little bit. And a very, very rich person got interested in the problem. David Shaw is possibly one of the top 100 richest people in the world. In fact, Jeff Bezos was one of his employees back in the day. So David Shaw, when he became, at one point realized he wanted to give back to science. And the problem he picked was this time scale problem, how to make MD run longer. So he designed a very special computer, a very special purpose computer called Anton. The first Anton was so special that it could, if I might be wrong here, especially since it's going to get posted on YouTube, but if I remember right, it could do only cubic periodic boundary conditions for a protein. And over the time, it has become very, very general. It can do a lot of things, and with Anton, it was breakthrough. So this slide is actually a slide from my qualifying exams at Caltech in 2009. And this is a problem that I love so much, and it's not far from getting solved. So, but back then they were able to get to a millisecond, and it was a science breakthrough of the year paper. Now 10 years later, I'm a stressed out, semi-stressed out assistant professor. Has this millisecond gone up in 10 years? The answer is a little bit, but not by far. So with millisecond, maybe you can study protein conformation change, but to study things such as crystal nucleation or the dissociation of a drug, the time scales that are of interest are so slow that just brute force computing is not going to do it. More so, this brute force computing is for classical models where you assume that atoms are talking to each other through springs and things like that. Fancy springs, but basically springs. While we know in reality that life is not that simple, we are all perhaps quantum. So people like to use polarizable force fields or do Born-Oppenheimer or Carr-Parrinello molecular dynamics or even fully quantum dynamics, where you account for the tunneling of hydrogen atoms. So as this is with classical force field, as we go to more and more complex force field, which is inevitable, it's going to happen, this timescale problem will persist. It will only become worse. So there is huge need for fun method development in this field. And that's where we get to the heart of my research problem, which is why is this timescale problem so hard? So people have been able to simulate systems in MD comprising 1 billion atoms, if not more. That's impressive. 1 billion atoms is almost a micrometer size sample. You can study a micrometer size sample in all atom resolution in MD, follow every atom, but only up till maybe fraction of a nanosecond, maybe a few picoseconds. So space is easy to parallelize mostly. There is complications with evolved sums and things like that, but you can deal with it. What you do is to break the system into chunks, and you have parallel computers take care of the different chunks. Time is a bit trickier, right? I could not have a group of 5,000 graduate students, although the 6 graduate students I have, they seem to work that hard. But I cannot just break them into 5,000 parts and say, you take care of t equal to 1, you take care of t equal to 2, and I will patch it all together. People have tried to do that. Vijay Pandey tried to do that. Arthur Hodel tried to do that, but there are approximations. So time is hard to parallelize. In fact, in order to predict the future, we need to know the past exactly. How do we do that? And more importantly, is it really true? For biological system, is it really true that we need to know the past exactly in order to predict the future reliably? And that's the key word here. And that gets us really close. So it's, as you will see why I'm really excited about today's talk. I should have mentioned it, especially because going after the last 2 talks, and you'll see the connections, the last 2 talks there. It's not just a passing connection, there's a huge connection. We'll see what they are. So timescale limitations can be surmounted if you knew something in chemistry which is called the reaction coordinate. just the most informative degree of freedom. So you must have seen such pictures in your high school chemistry book where you have a double well, or in your undergrad quantum mechanics, and you don't see GIFs in books. Maybe change with virtual training, but you have a system trapped in one basin, and it's undergoing thermal fluctuation. So an event that actually takes it to the other side is going to be a rare event. It will happen at some point, but the odds that it happens are very low, so you have to wait long enough. So this is, if you knew, so this type of a projection you can make for any coordinate. If you're a high dimensional system, you just marginalize out all these other degrees of freedom and you make such a prediction. But if just so happens that this is the main slow degree of freedom of the system, and we will quantify it soon enough, then you can play tricks from StatMech. One of these tricks is called metadynamics. Those who are familiar with statistics would recognize it as importance sampling. What you do is, to wherever you go in this landscape, you add a little bit of bias, you add a little bit of repulsive potential, and you start filling up the landscape. So at some point, the barrier that you experience is lower. In fact, if you keep running it, it becomes barrier-free. You don't want to run it to this limit because your protein will start to look like a spaghetti. You probably don't want that. So you stop at some point. And it's a cottage industry. Metadynamics has maybe 3,000 citations, and there are many other similar methods. If you add them up, there are probably more than 30,000 citations for methods like this, so-called enhanced sampling methods. The typical framework for all these is to pick such a low emission coordinate, then run this simulation, look at the bias you deposited, which gives you the free energy. And we saw this free energy in Alex's talk also in the first one. And if you're feeling brave enough, you can use methods such as this I published during my postdoc at ETH in Switzerland and PRL, where it allows you to get the unbiased dynamics from this dynamics. So you can go back and rescale to get what would be the dynamics if you did not fill it up. I'm not going to go into that. I'm going to tell you that this method exists because I will use it. It uses something called an acceleration factor. So in principle, all these methods are accurate. They will work in the limit of time tends to infinity. In practice, it's helpful if the orthogonal degrees of freedom are not slow. They are all fast. So this leads to a chicken versus egg problem. Or in order to know the answer, you need to know the answer. So in order to do the sampling, you need to know a good reaction coordinate. In language of importance sampling, the perfect zero variance estimator is if you know what you wanted to sample. However, how do you find the reaction coordinate if you haven't sampled the system? So what we want to do is to learn sampling methods that automatically learn the reaction coordinate as they sample the landscape. Now, this would have been my second pop quiz, but I can't do that right now, so I'll just go with it. So this is a quotation from a very favorite book of mine. I want you to think, if you maybe know where is this from. It says statistical mechanics does not tell us what the relevant variables are. This is our choice. If you choose well, the results may be useful. If you choose badly, the results, while still formally correct, will probably be useless. So this wonderful quotation comes from a book by Robert Zonzig. It's it is the best book on non-equilibrium statistical mechanics. It has a few typos, but which is kind of like keeps you alert. So in the chapter on projection operators, Zonzig talks about this, who was a professor at Maryland for a long time. So Zonzig says, don't even try. Well, let's try to see if we can prove Zonzig at least partially wrong. And to do that, we will take help from two very smart people who have both showed up in today's talk. One on the left is E.T. James. One on the right is Bill Bialek. He's no longer alive. He's, of course, alive and kicking. And I kind of think of this as my hair goals. You can see my beard. My stay-at-home beard is growing. I don't have hair on my head. So this reaction coordinate can be defined exactly, but uselessly. As it happens with many things, especially when a sufficient flux of mathematicians, sufficient quantum of mathematician enters the field, they show, oh, we can define it for you. But oftentimes these definitions end up being useless. In this case, it was not a mathematician, it was Gonzaga back in 1939 who defined such a thing. And people like actual mathematicians like Eric Mendeniden have worked with this closely in the last few years. And the idea is that you can define it using this notion of an isocommuter, which basically goes to phase space, launches a bunch of trajectories from different points, and counts what fraction of trajectories will go back to A, what fraction of trajectories will go back to B, and then joins these contours with the same probability, and the normal through these contours is the reaction coordinate. It's complicated. It's very hard to get in practice. There are methods that try to get it in an iterative manner, but it's difficult. So what we try to do, and I'm not going to talk more about this, but what I want to mention is that this opens up space for creativity. Creativity also means the freedom to be wrong. So we can be practical, but use approximate definitions. One such definition is something I introduced during my second postdoc at Columbia University with Bruce Bond, which uses this again idea from E.T. James, not maximum entropy, but maximum path entropy or maximum caliber. Second one that I'm going to talk about today is very much inspired by Alex's work called Past Future Information Bottleneck. So the idea here is, and you saw the information bottleneck, it takes an input, it compresses it into some coordinate, and it allows you to create an output. In our case, we are interested in dynamical systems. Specifically, we were interested in this paper by Susan Steele in the journal Entropy, which was called Predictive Information Bottleneck. So what we are interested in thinking of dynamical systems where, for example, imagine you're a frog and you're trying to catch a fly. So if you fixated on building a model for a system which just captures where the fly is now, then you will be a hungry frog, right? Because you will open your tongue and the fly will be gone from there. So a good model for dynamical system is one which allows you to predict the future slightly into the future. Or same for, this explains why my cricket career growing up in India failed, because I was fixated on catching the ball now, but not slightly into the future. Also, you don't want to predict too far into the future. If you predict too far into the future, your system will become Markovian, but it's not what's going on. You want to predict just slightly into the future. And in our case, we want to take these models, which, like, of course, Bill Bialek has applied to looking at retinal processing, and we want to apply it to seeing how biophysical systems evolve. So this chi is the information bottleneck, and our ansatz is that we can interpret it as a reaction coordinate. So let's see, how do we do that? And of course, it's a great honor to be giving this talk after Alex, because this was the paper that really inspired us. And then we started, so it's cited in all our papers. So that really got us going, how to do this. So we know there are two mutual informations now, and as Alex mentioned, and you saw Nicole also use it. If you set x is equal to y and beta is equal to 1, you recover a variational encoder. We are working in a general framework. In fact, we are also working with beta VAEs and things like that. I'm not going to go into that right now, but this is the framework we have. Someone asked about what does beta represent physically. Bialek has nice papers on how beta is, you can see phase transitions in the learning depending on the value of beta. So it's an insightful Lagrange multiplier. So here what we have is an input trajectory coming from MD, and we would like to learn a bottleneck for this trajectory, which can predict the output of the trajectory slightly into the future. That's the basic framework. It's easier said than done. First of all, you cannot compute this mutual information exactly. This mutual information, if you try to compute it exactly using, so you have an encoder which takes you from the input to the bottleneck, and if you wanted to compute this decoder exactly given the encoder, you have to use Bayes' theorem. And as you would recall, the Bayes' theorem has a denominator which blows up in order n squared. So that's the same partition function problem. So I love variational inference, and I really wanted to talk about it, even though in this audience many people know about it, because it's one of those things which is really in StatMech. In fact, a lot of machine learning people seem to acknowledge Feynman for his work in 1955 on this, but I would like to claim that Zwanzig has a paper in 1954, if you go and read up. It is actually much more cited than Feynman. So Feynman applied it to polarons, while Zwanzig applied it to liquids, and the same principle. And depending on the book where you read, if you read by David Chandler's the book on StatMech, you will see some abbreviation. If you read the book by David McKay, you will see a longer abbreviation. So a lot of people have thought of this idea. It's quite simple, which says that instead of working with the exact decoder, which is intractable, why not work with an approximate decoder? Sure, what do you lose by working with an approximate decoder? Well, your objective function is no longer the same, right? It's no longer the same, but it changes in a very special manner. The way it changes is that it gets incremented by a distance, specifically the KL distance, KL divergence, which you saw earlier. Without worrying about what this distance is, you would probably remember that any distance should have 3 or 4 properties. It should never be negative. It should be symmetric, and it should follow my favorite relation in math, namely the triangle inequality. This distance is kind of hopeless. It doesn't follow triangle inequality, I think. And it is not symmetric, definitely, which is scope for that research that we are working on. However, it is non-negative, and that's wonderful. This means that if you work with an approximate decoder, your objective function is guaranteed to decrease. This is your target objective function, but if it's an approximate decoder, you are guaranteed to work on a surface which is bounded by below, which bounds it by below. So here, the jagged line is the true decoder, which is very hard to find. You start with an approximate decoder, you go and optimize on this surface, you go and change your decoder, you go and approximate on that surface again, and you're guaranteed, you have a convex optimization problem now, in principle. You get to this convex versus concave in a bit. So this is a well-defined optimization problem. As long as you have a family queue of these variational approximations that are expressive enough. So in statistical mechanics, when we solve Ising model, we take the mean fit approximation, which you can solve exactly, but it's not as expressive. Or you can take neural nets, which are very expressive, but you won't be able to solve it exactly. And that's what we do here. And this is a nice paper that I like by Zach Lipton at UCSD, where he makes a remark about RNNs. I don't know how true this is, but it kind of gives the gist of it, that expressive power of a network grows exponentially with the number of nodes, while the complexity of both inference and training grows at most theoretically. So there is a benefit in using a deep neural net, and that's what we do here. So our architecture, which we published in Nature Communication last year, looks very peculiar. Our encoder we keep as a linear encoder. There is no reason why to stop at linear, but we start with the simplest encoder we can think of. And all this business we let happen in the decoder. Why do you do it? Because this way our encoder is interpretable. So these inputs, this could be some, go back to the protein that I showed you. These inputs could be some protein ligand distances. And if I pass a reaction coordinate, which is a ReLU or some hyperbolic tan encoder, based encoder, and my experimental colleague asks me, so what is the reaction coordinate? And I will be like, well, the reaction coordinate is the hyperbolic tan of some hydrogen bond. It's hard to manipulate. So linearity correlates with interpretability. So we have systematic ways of learning as to, so we start with a 1D linear encoder. Even there we run into optimization problems, which is what I'm going to show you next. But we have systematic ways of learning as to when should we extend the dimensionality of this linear encoder, or when should we add a new layer and learn more nonlinear encoders. But this is the framework. And of course, with a linear encoder, you make some sacrifices. You cannot just take the all atom coordinates. So we take different contacts, and we have a method for screening different contacts. I'm really not going to talk about this much, but this was work by Zach, who is a grad student, and Pawan, who is an undergrad, who's applying for grad school next year. I cannot recommend him any more highly, though I wish he would just stay with me. So we have a method which takes this input space and compresses it. So it makes the training life easier. This is all on GitHub. I will tell you the link later, which is called automatic mutual information noise omission. So given a set of order parameter, it learns a minimum number of order parameters that you should feed into such a method. So this is how the full algorithm looks. You do your MD, your system is trapped in some basin. So here you're looking at part of a messenger RNA called a riboswitch. Here you're seeing the ligand dissociate from it. So if you just ran MD, you can run it on weeks and weeks and weeks on a supercomputer. Nothing would happen. It would just stay stuck here. So forget that it actually dissociated. You have a starting trajectory where it just got stuck. You take this trajectory, you learn the information bottleneck. You take this information bottleneck to do metadynamics or some other sampling of your choice. Now you have more data where you might actually get the ligand to dissociate. You repeat your machine learning and you iterate until the features converge or your free energy estimates converge. You can read about this and the other methods. I really recommend these two papers. This is a review where we wrote this earlier this year, actually, summarizing the state of the art and many other methods that are mixing machine learning with molecular dynamics and spec, and this is our own work. So this is the basic framework. It's called reweighted auto-encoded variation base for enhanced sampling. The title came first because as a first-year assistant professor, I think I was listening to a lot of rave music, basically, but then we kind of came up with the full form. The reweighted comes for the fact that anytime you have a biased trajectory, you have to account for the fact that points have been generated spuriously. So you have to adjust the training weights over here, and that's done on the fly. So this I already mentioned to you. We use Amino to do that. And this is the main slide that I want to show you today, actually, one of the main slides before I show you some applications and stop, which is even with a linear encoder, we really start to experience the non-convex nature of the training. So here is a website from Stanford where you upload a picture. This is courtesy my older postdoc, Joao, who is now at Mount Sinai. You upload a picture and it generates a text. So when it works well, it works beautifully. Man in black shirt is playing guitar. Black and white dog jumps over top. Sometimes it doesn't work, and then it looks like this. Bunch of surfboards on the beach, right? Bunch of bananas are on the table. I hope you're laughing at this point, because otherwise, yeah, this is the bad part of virtual seminar. There is no feedback. Anyway. So it's kind of funny, but it's also sad. Now imagine you're designing a self-driving car, and it's really learning wrong things. Here the cat is thinking, group of people standing around a horse. Let's go and get belly rubs. bad idea, cat. Or instead of saying that a pigeon is on the beach, you think small airplane flying in the skies. In terms of self-driving cars, this might mean that instead of seeing a stop sign, you just accelerate. In terms of molecular dynamics, it's not as bad as accelerating at a stop sign, but it's kind of similar because you will learn a bad reaction coordinate and you start enhancing your sampling along a bad reaction coordinate, and you will never know whether you are doing the right thing or not. So to deal with this, and I want to show you an example from Alemi dipeptide, which is like the hydrogen atom of the simulation. This is collaborative work done with a very brilliant graduate student at Arvana Champagne, who I believe will be looking for postdocs soon. He's working with Emad Tajor-Kishida, and he visited our lab. He shows that if you stop the training at the same value of the loss function, you can get very different reaction coordinates just with some noise. This is a linear encoder. Imagine how bad the situation will be with a nonlinear encoder. The reason why this happens is because we are really running our simulations on undersampled trajectories. It's one thing to publish a mathematical proof and say that it's guaranteed to converge, but why would you use neural networks in this field on trajectories which are already sampled all the way? You might for dimensional reduction, but for enhanced sampling, you are for construction in an undersampled regime. So for this, we use our idea from the scoop method, and very briefly show it. This is unpublished work. It should be out in archive soon, where the idea is take different coordinates learned from machine learning and fit a cheap dynamical model to them. This model is called the maximum caliber model, and look for the time scale separation. The idea being that good coordinate will separate out slow mode from fast mode much better, like you can see over here, than a bad coordinate. And maximum caliber uses a simple square root type expression to do that. And now we can run RAVE, get different solutions, fit it through maximum caliber. As this plot, which I'm showing you over here, with the same loss function from AI, can often correspond to very different solutions in reality. If you really get it going to a very low loss function, you can get the right answer, but there's a lot of noise. And so there is two ways. Either you really run your optimization long enough, or you just run it short enough and use this method to get the best solution from that. And with this, I'm going to skip the applications part because I wanted to focus on methods, but as you can see, we can look at systems such as, this is a very popular test system in biochemistry of small ligand dissociation from protein. We can get rate constants in very good agreement with experiments. We can go and predict resistance mutations in the protein, which are the mutations which will make this drug, or in this case, a ligand, ineffective. And this is work which is currently, I think it's one of our best work, but it's no editor seems to agree. It's a long story. Maybe it will go somewhere. It's up on archive anyway, where we actually take this and do it all automated, starting with amino and RAVE, and show how we can predict what sequence, how sequence affects conformation flexibility in a protein 6 orders of magnitude faster than MD, and with minimal human intervention in a fully automated manner. So this work is on archive. You can go and see it. So I just want to conclude now. So I introduced mostly methods today. Amino was for selecting the inputs features for the encoder. RAVE was the actual process of iterating between MD and machine learning. And Scoop was the way of helping machine learning kind of scoop out bad solutions. All these codes are available on GitHub, Tiwari Lab. And I just wanted to mention that this is just we have just scratched the tip of the iceberg in this context of using a combination of statistical physics and AI ideas in chemical and biophysics. And there are lots and lots of open questions. This last question we also saw on Nicole's talk, and I think it's a very exciting time for people who did not hate their thermodynamics during undergrad. With that, thank you very much.
All right, thank you for a great talk. I'm trying to see if we have any new questions, either if you want to type them, or if you want to raise your hand, then we will try to find you, though we still have over 100 people on the line, so it may take me a moment to find you. So, okay, I see that we have a question that has appeared in the chat window. So this one is from John. So John, let me find you and unmute you.
Using some of these ideas, how far do you think they'll go in terms of solving the timescale or number of particles problem? How many particles, and how far into the future do you think you can eventually simulate these systems?
Yes, so very good question. So if you take our time only statistically true, in the sense that we are giving you a clock that is on an average correct. Once in a while it is very fast, once in a while it is very slow. On an average, our clock works well and can push you to time scales which are well within minutes, days, or hours, minutes, days, or even slower. However, this we are doing routinely, but a bit problem specific. So far we are mostly, and this is where this order parameter input selection comes in. So far we are able to tackle a lot of protein ligand and binding type problems, or protein conformation flexibility problems, and we are also starting to see some progress in crystal nucleation. So it's a bit problem specific, but it's not solved in a generic way. But for these domains of problem, which are very important, we are starting to get into any time scale that you would like to, only in a statistical sense. So I hope that answers your question.
Yeah, thank you.
Let's see. So we also have a question from Kevin Chen. So Kevin, I'm trying to unmute you, but you are self-muted. Okay, so Kevin, you can ask your question. Oops, you are muted again. All right, so I'll read your question.
Oh, okay. Does this work now? Great, okay, cool. Thank you for the great talk. So towards the end, you had a slide where you said the best reaction coordinate does not minimize loss. Can you briefly review again what best reaction coordinate meant and what the loss was?
Yeah, do you still see my screen?
Yes, yeah.
So what you're seeing here is that if this is a very, I love the slide. So it's unpublished, but so if you stop the training at the value of the loss function that you think is low enough, you don't really know what's low enough, right? For like in any global optimization problem, you might be very wrong. If you really run it long and long and long, you will be right. So I'm not saying that the loss function on its own is not sufficient. What I'm saying here is what you want to achieve here is that the bottleneck should capture as much of the slow modes as possible, and everything not captured by the bottleneck is as fast as possible. That's the notion of the spectral gap or time scale separation, which is very common in quantum mechanics and everywhere. So that's what we are showing here, is that even for this intermediate loss function, there are some of them which do the job well. So you don't really have to run it much longer to get to this loss function. If you run it longer, you would get to lower loss functions. So you can see there's some sort of correlation here, but it might be misleading. So in a way, it shows that, like Alex's very nice slide where he had a bunch of Lagrange multipliers, maybe we should add the spectral gap as another quantity in the optimization for our problem, yet another Lagrange multiplier. So there is some physics. This physics is time scale separation. And while the loss function is guaranteed to achieve it for infinite data, infinite training limit, for intermediate values, you might very well be getting stuck at a saddle point. That's what we're seeing here.
Right. Cool. Thank you.
All right. So I think we have time for one last question from Mike Gibson. So Mike, I just unmuted you.
Hi, Pratyush. That was really a fun talk. This is Mike Gilson at UCSD. Hey, so see you off Twitter here. Yeah, so as I understand it, the neural network is predicting, I guess, a confirmation, some time in advance, right? A short time delay. So I'm just curious, what do you find is the useful range of time delays for that?
So that's a very, very good question. So my wonderful student, Yang, who will be on the postdoc market in 2 years, wrote a paper in JCP here, where he studied this for model systems in great detail. And actually, if you still see my slide,
yeah,
I can show you. I thought, Mike, you're going to ask me some very difficult question about lysozyme. So for the simple systems such as alanine dipeptide, it doesn't matter what time delay you take.
Okay.
This is why alanine dipeptide often gets criticized in the enhanced sampling community. Everything works.
Yeah.
But for even benzene lysozyme, if you take delta t is equal to 0, you get it very wrong. So here the different order parameters correspond to. So here, as you can see in this legend, the last 3 are interhelix separation. So last 3 correspond to protein breathing, and the first 8 correspond to ligand movement. So what you see is that if you don't try to look into the future, it looks like the protein breathing does not matter. As soon as you go slightly into the future, you get a strong result that the protein breathing does matter. And it's quite robust, and we have some mathematical results as to why it's robust, but it's a work in progress. and I'm happy to talk more about that. I will send you the preprint. So in Journal of Chemical Physics this year, we looked at this property in a mathematical way. And so basically, it seems it's robust for small delays. If you go too far, our framework actually breaks down, so we can't even check too far.
Right. Yeah.
So that's
Okay.
what it is. So this is kind of a nice plot because it shows you just go slightly into the future. You don't have to screen all the time for which delta T to take.
Thanks.
All right, and so with that, I think that we are actually just about at time. I'd like to thank all of our speakers again, and also thank our audience for attending. And please, everyone, if you're not already a member, please join GDS, and we'll see you next time. All right, with that, goodbye and enjoy your weekend.